Welcome back. In the last lecture, we discussed the flows at low Reynolds numbers. Today, we will deal with flows at large Reynolds number. We start with the normalized equation for the flow past a circular cylinder. Here, each variable has been rendered dimensionless by normalizing it with respect to a characteristic quantity. When Reynolds number is large, the viscous terms become small and can be neglected. With this is the form of the governing equation. In this, we have combined the gravity and the pressure terms to deal with a non-gravitational pressure. For steady flow with no free surface, the equation reduces to V star dot del star V star is equal to 1/2 delta star P star, where delta Pc, the characteristic pressure difference, has been taken as 1/2 rho V naught square. This equation is known as the Euler equation. This is a first order equation and would accommodate only one set of conditions on the boundaries. But on stationary solid boundaries, we have two conditions. Both the normal and the tangential velocities must be 0. If we solve the Euler equation and obtain the Inviscid solution and apply the no penetration condition, that is the normal component of the velocity at a solid stationary surface is 0, we would get a velocity profile that varies something like shown. Clearly, this would result in a slip at the wall. The velocity at the wall is this rather than 0. This is clearly unacceptable. And as we discussed a few lectures ago when we were discussing the process of approximations, that this difficulty is resolved by assuming a thin boundary layer near the surface. In this thin region, the viscous effects are not negligible and the no slip condition is applicable at the wall. We had shown that the velocity would rise very sharply from 0 at the wall to a value very close to what the value would be in the inviscid flow at the wall. The two parts of the velocity profile would merge to give a smooth velocity profile. The thickness that we shown here is exaggerated. The boundary layer thickness, we would learn later, is of the order of 1 over under the root Reynolds number. So, for a typical Reynolds number of 10 raised to the power 4 or 10 raised to the power 5, the boundary layer thickness is of the order of 10 raised to the minus 2 of the characteristic dimension of the body. The boundary layer on a bluff body plays a central role in the dynamics of fluid at large Reynolds number. We will explore it in some details in a later lecture. Let us consider the flow of a fluid at a very large Reynolds number. In that case, the boundary layer in the front half of the body would be thin, but this boundary layer would separate near the shoulder or slightly ahead of the shoulder and the flow behind the cylinder. In the wake of the body would be disturbed, would have viscosity playing important part. So, separation is the culprit in this case. If, however, we have a streamlined body like an aerofoil, we, the boundary layer develops in the same manner, but the separation is delayed. And so, the wake is much smaller. Most of the flow around the aerofoil is an inviscid flow region. It is for this reason that the theory of aerodynamics is built largely as an inviscid flow in the first approximation. There are a couple of reasons why this holds. One is the boundary layer is very thin. Second, as we shall show later, the pressure across the thickness of the boundary layer does not change. That is del P by del N, normal to the surface within the boundary layer, is approximately 0. Therefore, the pressure at the edge of the boundary layer approximates the pressure that impresses on the surface itself. Since the boundary layer is thin, over most of a surface in a streamlined body, we may extend the inviscid flow right up to the surface as a first approximation. That's why in aerodynamics, we neglect the boundary layer completely, solve for the inviscid flow right up to the surface of the aerofoil, calculate the pressure from the inviscid flow and assume that that is the actual pressure distribution on the surface of the aerofoil. Even though the Euler equation which governs inviscid flow is a first order differential equation, it is non-linear and its solution is not straightforward. But there is a class of flows, as shall be seen here, where only a linear equation needs to be solved, and these are amenable to solutions by the method of superposition. This class consists of what are termed as irrotational flows. We had seen in an earlier lecture that the rotation of the fluid element can be measured by averaging the rotation of two perpendicular lines, and that is obtained as rate as omega is equal to 1/2 of delta v by delta x minus delta u by delta y, where u and v are the component of velocity in the x and y direction. We can write similar expressions for the x and y components of the rate of rotation. These are readily recognized as 1/2 of the components of the curl of the velocity vector. Thus, the vector omega, which is the rate of rotation vector with three components omega x, omega y and omega z, is 1/2 the curl of v. We may note that quite a bit of scientific literature where the symbol omega is used for the vorticity, that is for the curl v itself, quite unlike here where we use it for the angular velocity, that is 1/2 curl v. So be careful about what notation we follow. If this is a path line on which a particle is moving, a rotational flow is one. That if we could imagine a paddle wheel moving along the path line, the paddle wheel would rotate. And that rotation is largely because of velocity gradients. A rotational flow does not need to have a curvilinear streamline. For example, this flow within a channel made up of two walls, lower wall stationary and the upper wall moving with the velocity v naught. There is a velocity variation from 0 at the lower wall to the velocity v naught at the upper wall in the steady flow. A paddle wheel floating down this channel would move in a straight line. But since the velocity near the upper wall is larger than velocity down below, this paddle wheel would have a clockwise rotation as shown. So this definitely is a rotational flow. On the other hand, even if the streamlines are curved, it is not necessary the flow be rotational. If I have a flow in which the velocity varies like k divided by r, v in the theta direction is k divided by r inversely with radius, the flow is irrotational. A paddle wheel moving along the fluid path would not be rotating about its own axis, and so the flow is irrotational. The rate of rotation of a fluid element is related to its angular momentum, and the angular momentum must remain constant unless a torque acts on it, second law of Newton. The only way a torque can act on a fluid element is through the action of shear forces. If the shear forces are negligible, then there is no torque acting on a fluid element, and the angular momentum of the fluid element must not change with time. Thus, inviscid flows, which are irrotational to begin with, will remain so. Whenever a fluid is induced to flow due to gravity or pressure forces, as in rivers, channels, over weirs, in hurricanes, etc., the flow is largely irrotational as long as we keep away from the wall or encounter large velocity gradients where viscous effects start dominating. When a real fluid flows past a streamlined body at high Reynolds number, the region outside the boundary layer can be taken as inviscid, and since the velocity field upstream is uniform, every fluid element has no rotation to begin with, and with the absence of the viscous stresses outside boundary layer, this ensures that it cannot rotate as it moves downstream. The flow outside the boundary layer is therefore irrotational. Within the boundary layer, however, the action of viscosity rotates the fluid element, and with it the paddle wheel, if a paddle wheel was present. It should be clear that the solid surfaces submerged within a fluid contribute to setting up the fluid adjacent to them in rotational motion. These regions of rotational flow travel downstream with the fluid and gives rise to the regions of rotational flows embedded within the large expanses of irrotational flows. Thus, within the boundary layer, rotational flow develops, and this is the source of rotation. Ultimately, these rotational flows shed in the wake, but for streamlined bodies, the wake is thin. So this region of rotational flow is limited. Irrotational flows have some special properties which render the equations governing them linear, and therefore these flows have been studied in great details. Before doing this, we introduced the concept of vortex lines and circulation. These two concepts play very important role in irrotational flows. A vortex line is defined just like a streamline. It is a line which is tangent to the vorticity vector. The vorticity vector is omega is equal to curl V, and at every point the vorticity vector is tangent to a vortex line. A vortex tube is a bundle of vortex line passing through a closed circuit C. Imagine a circuit C as shown. From every point of this, we pass a vortex line, and so this vortex line would occupy a tubular region in space, and this tubular region is termed as a vortex tube. We shall later see that an important property of vortex tube is that a vortex tube either closes on itself or extends to the boundaries of the flow. Here we have shown a smoke ring gun. It is made of a container in which smoke is filled, and there is a diaphragm at the back where we tap and a smoke ring comes out. The smoke rings are regions of vorticity. Donut shaped vortex tube. Shown in the right is the pattern of the flow in these. If we take the central axis of this donut, we see that there is a vorticity vector tangent to it at every point. The strength of the vortex tube is defined by the product of the vorticity normal to the surface enclosed by the curve C. So in this curve C, if we take a small area dA, then the strength of the vortex tube is the integral over the capping area of omega, capital omega times dA, where capital omega is the vorticity vector, curl of V. Thus, the vortex tube strength is equal to the normal component of vorticity integrated over the area of cross section of the vortex tube. Some texts make a mistake and describe this vortex strength omega dot dA as the flux of vorticity through the tube. It is wrong in the sense that this vorticity is not flowing through the tube. It does not flow through the tube. So there is no flux. It does not enter the tube. Those of you who are familiar with the calculus of vectors know that Gauss's theorem relates the integral of a vector quantity over a closed circuit to the surface integral of the curl of that quantity over a surface capping the circuit. Thus, for the vortex tube shown, the strength of the vortex, which is the integral of curl V times dA over the area capping C, is equal to the line integral over the closed circuit C of V dot ds. That becomes the tangential component of velocity along the circuit. Thus, the strength of the vortex tube is equal to the integral of the tangential component of velocity around a circuit enclosing the tube. This is interesting development because there is a name for this integral over the closed circuit, and that name is circulation. Integral V dot ds over a closed circuit C is termed as the circulation gamma, with the integration proceeding in the counterclockwise direction. The circulation about a circuit equals to the vortex strength of the vortex tube formed by the vortex lines passing through each point of the circuit. So we start with the circuit C, then the circulation about the circuit C is equal to the vortex strength of the vortex tube formed by the vortex lines passing through each point of the circuit. Another important property of vorticity is that there is no component of vorticity through a closed surface. That is, if capital omega is the vorticity vector at any point, then omega dot dA integrated over a closed surface, a surface enclosing a volume, is 0 if the flow is rotational. And for this, we require the divergence theorem from the calculus of vectors. The divergence theorem states that if we consider a volume V bound by a closed surface S, then the integral over the bounding surface of curl V dot dA is integral over the volume of the divergence of curl V dV. The right hand side of this expression vanishes since the divergence of curl must be 0. Curl is perpendicular to the divergence vector, and so divergence of curl must be 0 identically, and therefore we get the net component of vorticity through a closed surface as 0. We'll use these facts shortly. Now, one of the important properties of vortex tubes is that the circulation is same in all circuits embracing the same vortex tube. Consider a volume which is part of a vortex tube shown. The enclosing surface of this volume is broken up into 3 parts, 1 and 2 as the cross section of the vortex tube, and third is a surface of the vortex tube itself. So surfaces 1, 2 and 3 enclose a part of the vortex tube. Now, the net vorticity at the surface through the closed surface must be 0. Since the surface 3, which is tangential to the vortex tube, is a vortex surface in the sense that the vortex vector is parallel to these, tangent at every point of the surface. So the vorticity through this surface is 0. So V vortex dot dA, vorticity dot dA over surface 1 must equal the vorticity dot dA integrated over the surface 2. That is, the net component of vorticity across each cross section is the same in inward at one and the outward at other. And since this normal component of vorticity is the strength of the vortex tube, and the strength of the vortex tube is the circulation. So the circulation is the same for all circuits embracing the same vortex tube. In other words, the strength of the vortex tube remains constant along its length. And if this be so, this implies that a vortex tube cannot terminate within an inviscid fluid. Thus, if I have a vortex tube, it cannot end within an inviscid fluid, because what happens to the vorticity after that? So, it must either close on itself like a vortex ring or extend to the boundaries of the flow. After persisting for a while, a smoke ring diffuses away. This is because of the viscous action over time. Another example of vortex tube ending on itself is the vortex pattern on an aircraft wing, which forms a complete circuit consisting of a U-shaped vortex and the starting vortex left at the airport. This is a typical pattern of vortices on an aircraft wing. We assume a bound vortex on the wing. In fact, it is this vorticity that is supposed to produce the lift. The Prandtl's theory of aircraft wings is based on this assumption that there is a bound vortex with the wing. There are two trailing vortices and a starting vortex. I'll show a little bit later the development of the starting vortex. But then this bound vortex in two longitudinal vortex, which are called the trailing vortex, and this starting vortex form a closed loop of vorticity, of vortex tubes. This picture shows the vorticity trailing from the edges of the aircraft wing. Another view of these trailing vortices, we are looking behind the aircraft and the smoke is swirling around, showing two distinct vortices at the two wingtips. And there is a starting vortex. As the aircraft wing moves, a vortex is formed which is bound with the wing, and there is a vortex which is termed as a starting vortex and is left behind at the airfield. Further properties of vortex tubes. The relationship between circulation and the area integral of the vorticity is only valid if the region enclosed by the contour C is simply connected. This means that the region must be such that it is possible to shrink the contour C to a point without leaving the region. So a region with a hole like a bathtub drain is not simply connected, since any contour that we take around it cannot shrink to a point. The bathtub drain would come in between. Similarly, a flow about a two-dimensional body is not simply connected. This circuit C shown here cannot shrink to a point. The presence of this yellow body would forbid that. Of course, this is possible only in two dimensions. In three dimensions, if the yellow body was a three-dimensional body, we could have a capping surface on C which avoids the solid body, and this contour could shrink along the capping surface. Another property, the circulation about any circuit enclosing a 2D body within an irrotational flow is the same. This is easy to show. Consider a 2-body and 2 circuits C1 and C2. Neither C1 nor C2 can be shrunk to a point, but we can artificially create a composite circuit, slit the space between the 2 circuits by 2 straight lines L1 and L2 and connect them to C1 and C2 in the manner shown. Now, the circuit which consists of L1, C2, L2 and C1 is a circuit which is reducible and which lies totally within an inviscid flow. We can shrink this to a point, and that point would lie within the inviscid flow. It avoids the 2D body completely. And so the circulation about this should be 0, since this lies wholly within the inviscid flow. There is no vorticity which is enclosed. Now, the circulation produced by the component L1 and L2 cancel out because they are in the opposite direction. So, this shows that the circulation about C1 and about C2 must be the same. Circulation about a circuit that lies within inviscid flow is the same for all circuits going around a 2D body. There is a famous theorem called Kelvin circulation theorem. We will not prove it here because it takes a little higher level of vector calculus, but the theorem is easy to understand. The circulation around any material loop in an inviscid and incompressible fluid does not change with time. Consider this circuit as a material loop. This is the position at a given time t. At a time t plus t, the same particles occupy this new location. These are the same material particles. So we say the circuit is a material circuit. Then whatever be the circulation of this loop, of this circuit, at any given time remains constant with time. d gamma by dt is 0. Note that this being a material circuit is important. And this gives an interesting conclusion. Consider an aerofoil sitting in an inviscid fluid. There is no velocity anywhere. I draw a circuit C. Clearly, since the velocity is 0, the circulation around this circuit is 0. Now let us assume that the fluid starts moving to the right. as the fluid starts moving to the right, this circuit would stretch and would occupy a position like this. I replaced that aerofoil by a picture, a photograph that was originally produced by Prandtl himself in his laboratory. And in this photograph, you see a vortex out here. So there is vorticity now that is induced there. The science of aerodynamics as developed by Prandtl talks about the origin of this vortex, which is termed as the starting vortex, which we talked about earlier. Now, the circulation about this white circuit that we've shown here would still be zero because it's the material circuit. So how about this vorticity? Divide the circuit into two circuits, C1 and C2. The original circuit C was nothing but C1 plus C2. The contribution to circulation about these two arms cancel one another out. They are close together. Around circuit C2, there is a positive circulation because the flow around the starting vortex is counterclockwise. So there is a positive C2. Now, about the circuit C1, then there should be an equal and opposite circulation because the net circulation must still be zero. This circulation is due to what is termed as the bound vortex with the wing. So the wing has a circulation going clockwise. This is the bound vortex, which is one arm of the closed vortex circuit behind an aircraft wing. Imagine a circuit on the vortex surface. Since the vorticity on the vortex surface is tangential to the surface, the circulation about this circuit is zero. If we follow the material that constitutes this circuit, the circulation about it is always zero by Kelvin theorem. This is true for any circuit on the vortex surface. Thus, the vortex surface is a material surface. So whatever is a vortex surface once will always be a vortex surface in any rotational flow. Since the surface of a vortex tube is a vortex surface, a vortex tube is a material tube, always constituted by the same material particle. Thus, a smoke ring, a vortex tube closing on itself, is a material tube. That's why we see as a tube of smoke, the same smoke always. The intersection of two vortex surfaces is a vortex line, and it follows from the above that this too should be a material structure. Thus, a vortex line is a material line. For the special case of a vortex tube with small area, the vorticity omega can be considered as approximately uniform across the tube cross-section A, and the strength of the vortex tube can be written as gamma is equal to omega times A. Therefore, if we stretch the vortex tube, and since it is a material tube, It consists of the same material. If we stretch it, its cross-sectional area will decrease. And so this vorticity along a vortex tube varies inversely as the cross-sectional area of the tube. This clip shows a ballerina. The ballerina is spinning around, and as she stretches herself by raising her hands, the speed of rotation goes up. That's exactly how the vorticity along a stream tube increases. This has been illustrated very nicely by Professor Shapiro of MIT in a movie, Vorticity 2, produced by him for the National Committee of Fluid Mechanics film in 1964.
To show the effect of stretching vortex lines, we have an apparatus in which water flows over a hump. The water depth first decreases and then increases. The speed of the water is inversely proportional to the depth, and so the flow accelerates as it goes up the hump and then decelerates as it goes down the hump. Now I'm making a vortex with a sharp-edged plate. This vortex has its axis vertical. As it goes up the hump, the length of the vertical vortex line decreases, and so the vorticity decreases, as you can see by the spin. When the vortex line goes down the hump, the length of the line increases, and the rate of spin also increases.
Thank you very much.